great. So for composite conductor material or composite conductor, we use a number of conductor materials. For example, steel core aluminium conductor. Steel core aluminium conductor means steel is at the core to make the conductor strong or increase its strength, tensile strength. Steel has more tensile strength as compared to aluminium. Aluminium's tensile strength is much less than the tensile strength of steel. So that's why you put steel at the core, and around the core, around the steel, we put aluminium conductor. Now these two different materials are responsible for different purposes. Aluminium is supposed to carry the current, not for making the conductor strong. While the steel at the core is responsible for making the conductor strong enough, meaning it increases the tensile strength of the whole conductor. So for composite conductors, we have different materials and they will expand with increase or decrease in temperature from ambient in different manner. So it becomes very difficult to calculate sag using some empirical formula. Now that is why when we deal with composite conductor in real life transmission line applications, we cannot calculate it easily. So what happens, the manufacturer of those conductors, they provide us with a chart. We call it sag and tension chart. We call it sag and tension chart. From that sag and tension chart, we look at the various parameters and we can get the amount of sag that we will have if we string a conductor in between two adjacent supports for a certain length. Maybe the span can be 200 meter, 300 meter, or 400 meter. But for homogeneous material, we can learn that part in these days. But we need to remember again that in modern days, like these days, we never use a homogeneous material or homogeneous conductor for transmission line at all. But it's for learning purposes, we going for this one. Apart from that, we also need to consider another thing, which is the span, meaning the distance between two supports, the horizontal between two supports. Like for example, we have two supports there that you can see on the diagram. One at A is labeled as A, the other one is at B. Two supports of same height, the land is plain, the topography is not uneven or rough. It's the same level where the supports are installed, and then they have the same height as well. So two supports at the same level and same height, they are labeled as A and B. Now the horizontal distance between them, these two supports, is the span. We also need to look at the span. Is it 200 meter, is it 300 meter, or is it 500 meter? If the span is too much, we use different method. But if the span is within a certain range, for example, if it is up to 300 meter, then we use a method called parabolic method. Then we use a method called parabolic method that you see there on the screen. And we also use parabolic method when we find that sag is not exceeding 5% of the span, meaning if this is our span, this is small l, the span is small l, and the should not be 1.05 times of L. In that case, we don't do. The reason is one thing we need to again remember, that the span is smaller than the actual length of the conductor. The span is smaller than the actual length of the conductor, or the other way you can say the actual length of the conductor is always greater than the span. The actual length of the conductor is always greater than the span. So we get some sag. If the sag is not exceeding by 5% of the span, then we can use this method, which is called parabolic method. And for that parabolic method to calculate sag, expressed here in this equation that you can see, delta. Sometimes we can write S or some other variables, but we need to let us know, or let the readers know what is what. So delta is the sag here in this equation. W The small w that you see is the weight per unit length. W is the weight per unit length of the conductor. And L, small l is the span, meaning the horizontal distance between the two adjacent supports. And capital H that you see there is the tension that is working on the conductor. H, the tension that is working on the conductor. Now, this formula was derived by considering the moments that happen. For example, what we see here, that we have a conductor that is strung or suspended freely in between two supports A and B. There is a conductor that is freely suspended or strung in between two supports A and B, and there is the lowest point of the conductor, which is denoted by O. And these two supports are at the same level, they are of same height. Now, when that happens, if we remember that we discussed or we agreed that the conductor is of uniform weight, meaning its weight is uniformly distributed across its length. The weight is distributed across its length uniformly, meaning weight is going to be kg per meter. So when a conductor with uniform weight distribution is suspended freely in between two supports, as for example A and B as shown on the diagram, the conductor is going to take a shape like parabola, and that is what we see here, and that is why this method is called parabolic method. So this is called parabolic method. The reason is that we have suspended a conductor in between two supports A and B, which are at the same level and of same height, and the conductor takes the shape of a parabola due to its weight. Now, this weight is not only its own weight due to conductor material, it also considers the weight that comes into the scenario due to ice deposition on it during cold winter, and also other factors maybe in some cases. So we have three factors here that we see for the sag calculation using parabolic method: is the weight of the conductor, span, and the tension working on the conductor. Now, from these three factors, we can see weight is directly connected to the sag. So sag will increase if we increase the weight of the conductor. Meaning, if we use a heavy material, for example, copper or aluminium. If we use copper or aluminium, which one of these two, copper or aluminium, has higher density or higher weight? Copper or aluminium, which one has higher weight? Which material, copper or aluminium, which give us more? So copper, because its density is higher than the density of aluminium. So we know that when we are going to use copper, so it will have more sag for the same length. L, small l, the span is constant. So when we choose that, we need to know that if we use aluminium, then we will have less sag as compared to copper. Now, for L, the span, we see it's L squared. So it is directly proportional to the square of the span. Meaning, when we increasing span, the sag will increase in the square mode. Now, the tension, if we increase the tension, the sag is going to decrease. Meaning, this curve will become like this, or it will come closer to that straight line between that horizontal straight line between A and B. So these are the things. Now, how do we get that equation WL square over 8H? Sometimes we also write T, capital T, instead of writing H for tension. It depends. So what we do here, we consider all these things, and we consider the tension that is working at these two supports. Like when we string a conductor in between these two supports, the tensions mainly are here, and then some horizontal tensions will be working on each and every point of the conductor that we can imagine. So tensions here, TA, tensions there, which is TB, capital TB, capital TA, and horizontal tensions will be there at each and every point from A to B, everywhere. And then we also need to consider that point we discussed, and remember that point O is the lowest point of the conductor, and it is also the middle point of the conductor because its weight is uniformly distributed, and the supports are on the level plane, and the supports are of equal heights. So that is why this lowest point of the conductor is the middle point of the span L, and because of that, we can consider the moments or the tension that is happening now into the system. And if we take the moments about either of these 2 points A or B, we can equate them, and after equating them, we can find out the expression of sag delta is equal to WL squared over 8H. We can derive that. Now, what we can do to derive that equation delta is equal to WL squared over 8H, let's consider any of these 2 points, A or B. But it does not matter which one we consider only one, because they are same on either side of this point AO, which is the lowest point of the conductor or the middle point of the span. Because if we start from here and go that side, it's the same as if we start from here, we go to the point B. So we can take the moments about point B or point A, does not matter, but we stick to only one. So if you consider that, the moment we get the forces acting on it and the distance. So for example, the force is horizontal here and is acting on that vertical distance, H times delta. So H times delta is the weight, the force and distance here. H times delta is the force and distance here. And on the other side, what force is working here is the WL over 2, because this is the length of the span and W is the weight per unit length, so the total weight is WL. But for this portion O to B, because we consider the moments about the point B, so the length here is WL, and if we consider that the weight of that portion OB will be acting vertically downwards through the middle point of this OB. So it will be this distance, which is L over 4, and the del weight we get here is WL over 2. So what are the forces and distances there? Which is WL over 2, which is the force acting vertically downwards, and the distance is L over 4. So if we equate these two moments, H times delta is equal to WL over 2 times L over 4, we will arrive at this equation WL squared over H times 8. So WL squared over 8H is the general expression for sag, and into that weight, the weight of ice will come into that weight. The wind force will come into the scenario as well, and this is the tension that acts on the conductor, and that is the tension because of the tensile strength factor of safety that we choose. Is that okay? Okay, let's go to the next slide. Now we're coming to the point to look at again what are the things that are on the conductor. First of all, we say it's loading on the conductor. The other day I said when we talk about the word loading in electrical engineering, we consider the electrical loading, which is ampere, amount of current that is flowing through a conductor is the electrical loading, or sometimes we call how much watt, how many watts or megawatts, kilowatts, that's also loading. But when you're talking about sag and tension, or considering the mechanical aspects of a transmission line, then we talk about the mechanical loads that are on the conductor. The first one is the conductor weight. It is obvious, no matter what material we use, no matter if we are using one material or a number of materials to make the conductor, that is going to be there. On top of that, what can come in during cold winter, ice loading can be appearing into the system or into the equation of conductor sag calculation. So we don't get it every time. During summertime, it's not there. During winter time, it might not be there, but if the winter is too cold, ice is getting deposited on the conductor surface. And apart from that, we get wind blowing onto the surface of the conductor from time to time. If it's strong, very high speed or high velocity wind is blowing onto the surface of the conductor, we get wind loading. So these are the forces that act on a conductor. We call that loading on conductor. Is that clear? Now coming to the ice loading, because for weight of conductor we talked about it. For ice loading that you see on the diagram, what happens, this is the white portion, white circle is the conductor. It's uniform, made circular, but in practice it's not 100% circular, because we don't use one conductor, one strand. We call them strands. Like if you open the insulation of a cable that you use at home for various electrical purposes, then you'll find very small diameter strands are there, a number of them. Sometimes you will fail to count exactly how many strands are there. So each of them are called strands, like each of them is a single conductor. We put them together to increase the current carrying capacity of the cable or the wire. So each of them actually is circular, but when we use a number of strands to make a larger ampere capacity cable or conductor, is no longer circular. But for simplicity, to make our equations simple, we consider that they are circular. Again, around that circular conductor, which is having a diameter of small d, the ice deposition is happening here, which is shown by the gray color. So ice cover is here, which has a thickness of small t. Now, when we consider that thickness of small t for ice cover around the surface of the conductor, in real life, it's not uniform like that, not perfect like that at all. It's completely different from the ideal condition. But again, for making our equation simple, we consider that thickness T is same all over the surface of the conductor and uniform all over. So if that happens, then we get the equation of weight of ice loading, which is indicated by the plus Wi, meaning weight due to ice cover or ice loading. Weight due to ice loading, I is for ice. And then the equation is pi t times d plus t times rho I. Pi t, pi is that constantly, and then t is the thickness of ice cover, and d is the diameter of the conductor, and rho I is the density of ice. Rho I is the density of ice, and we must remember that loading again is uniformly distributed along the length of the conductor. So again, it's kgf per meter. Sometimes I used to get this question from the students attending this session, that why that f is there, kg per meter. I put that f there to remind me that it's weight, it's force. Weight is nothing but force. So f is there for force. That's what it reminds me all the time, because kg we use it for the unit of mass and weight, but there is a difference between mass and weight, if you remember from the school life. So that's why I put that f. So kg per meter or kgf per meter, whatever you want to write, you can write. It's not a problem to me, but you have to remember this point, that it is force. This kg is not going to be mass if I write it kg per meter. So that's the ice loading. That's how we calculate from the formula pi t. The pi is d plus t times the density of ice deposition. So it's uniformly distributed along the length of the conductor. Then the next one is the wind loading, and again you see that the conductor diameter is T, and wind is going to act on it from that side of the conductor. So wind is blowing onto the surface of the conductor. It might happen then that the conductor is having the ice deposition as well, meaning it's a very cold winter. Ice formation happened over the surface of the conductor. At the same time, some wind is blowing onto it. And in that case, we get the wind loading, and that you see there H, and it is horizontal because wind is going to act horizontally onto the conductor surface. So WH is equal to D plus 2T times P. And again, the D is the diameter of the conductor, T is the thickness of ice covering, and small p is wind force that is working on the surface of the conductor. P is the wind force that is working onto the surface of the conductor, and that it again, this wind loading is coming in with the unit of kgf per meter. Is wind force of kgf per meter uniformly distributed along the length of the conductor. Now, when you're considering the wind loading, as you can see, what happens here, if the situation is that it's summertime, there is no ice deposition on it, so thickness of ice T will be equal to 0, but the equation will convert to D times P. Can you see that? If we consider that summertime there is no ice deposition, only wind force is working on the conductor, so T will be equal to 0. And if we go back to this ice loading, that is summertime, again there is no ice deposition on the surface of the conductor, then T will be equal to 0 and Wi will be equal to 0 straight away. So there might be different situation on the conductor loading, the conductor weight, ice covering, wind loading, but the conductor weight will always be there in at all the times. We will get the conductor weight. Ice loading will come in some situation, wind loading will come in some situation. In some situation, we will get ice loading and wind loading, both of them. Is that clear? Okay, let's go to the next slide, which is showing the effective loading on the conductor. Now, what are the loads that we saw in a conductor? The weight of the conductor itself in the first place is going to be there all the time. Then the ice loading. If the winter is too cold, ice formation is happening on the surface of the conductor, we will get ice loading, and that will act vertically downwards. So that's why we show the conductor weight. Here I even showed that WC, meaning weight due to conductor itself, the weight of the conductor. WI is ice loading, and horizontal loading will come from the wind blowing over the surface of the conductor. So WC, which is the conductor weight, acting vertically downwards, WI, which is the ice loading, acting vertically downwards, and wind force WH is acting horizontally. And from that we can get this resultant. You know the formula from your mathematics, applied mechanics, everywhere. This is the resultant weight. WR, R is for resultant, so WR is the resultant weight, and we can use that WR in that formula that we had earlier, WL squared over 8H. And sometimes we need to know the vertical component of sag, because now the sag is not going to be vertically downwards, it will deflect because of this presence of wind loading which is acting horizontally. So we get the effective loading on the conductor considering the conductor weight, ice loading, and wind loading. Is that clear? Okay, let's go to the next one. Now we want to just look back again. We discussed all these things, but we want to look at them again. Factors that affect safety. Sorry, the factors that affect sag of a conductor. First of all, the conductor weight, and that conductor weight is due to the material that we use for making the conductor. The span, if we increase the span, the sag will be more and more. If we increase the tension, then the sag will be less. If we have more wind force blowing onto the conductor surface, then we have increased sag, and the deflection will be happening as well, because wind force acts horizontally on the surface of the conductor. And then the temperature, due to change in temperature, not for causing a change of season, summer to winter, but during summer time, during the day the temperature is high, at midnight the temperature is low. Because of that variation in temperature, the conductors expand or contract due to the expansion coefficient and its properties. So the change of actual length of the conductor will happen, and that will increase or decrease the sag as well. So these are all the factors that affect the sag, and we need to remember that all the time when we consider the sag. Now I'm coming to the next method, which is called a catenary method. We talked about the parabolic method, meaning when we have a conductor of uniform weight distributed along its line length, and we suspend it freely in between two supports that are at plane level and of equal heights. The lowest point of the conductor happens at the middle point of the span. Then we see that the sag can be expressed as delta is equal to WL square over 8H, and W considers all the loading on the conductor starting from conductor weight, ice cover, and wind loading. But we need to remember that we consider that the span for parabolic method is limited up to a length of or a distance of 300 meters. Now in these modern days, we doing the electrification all over the world, bringing electricity to the remote corner of a village, and we need to put more and more transmission lines to save money. We increase the distance between two towers. In other words, we trying to save money by reducing the number of towers, meaning we increasing the span. As we increase the span, the sag will be more and more. And we can do that by keeping the ground clearance enough, that is stipulated by the government regulations. So if we use longer spans, more than 300 meters, it becomes erroneous if we still want to use the parabolic method. And that is why we use a method called catenary method. And we call it catenary method because the conductor that is suspended between these two supports A and B takes the shape of a catenary. When we hang it freely due to its own weight, it will take that shape of a catenary, and that is why we call it catenary method. In the notes that I put on the Moodle website, it has shown all the calculation. It's a complicated steps doing all these derivatives and things. We get the equation for that one, and in this one we calculate the actual length of the conductor. We can calculate the tension at any point of the conductor as well. Although it's a complicated method, the reason we sometimes use it is that it gives us much more clear picture as compared to the parabolic method. In parabolic method, we just know the sag, which is WL squared over 8H, but in this case, we know the actual length of the conductor, we know the tension at any point of the conductor, we know the maximum tension where it is happening, and all the stuff. So we follow the same thing. We consider the horizontal tension that is at the lowest point of the conductor, which is O. We consider the width of the conductor, and we consider the pressure T that is happening here horizontally on the conductor. So we take a portion again, half of it O to B, and then we consider any point on the conductor P, and then we consider the tension that is happening, and then we do a lot of calculation that you can follow from the notes. I'm not going to go through all the steps of calculation, but finally what we find out is that sag at any point that can be derived as, let me go and show you the equations. You can find out the sag to be like this: delta H over W cos hyperbolic WL over 2H minus 1, tension T we can calculate, and the tension equation is not shown here. Tension equation is actually H cos hyperbolic times Wx over 2H. So that's the formula for tension, and we can calculate the maximum tension, which will come H cos hyperbolic times WL over 2H. We can calculate the length of the conductor, which is 2H over W times sin hyperbolic WL over 2H. So we can calculate sag, we can calculate tension, we can calculate tension at any point on the conductor. We can calculate the maximum tension that is happening. We can calculate the actual length of the conductor, capital L. We are using small l for the span. We are using capital L for the actual length of the conductor. Different. Capital L is greater than lowercase l. We must remember. And when I'm talking about this small l, capital L, when you use such variables, same letter, uppercase, lowercase, we always need to tell the reader that this is this, meaning small l is the span, capital L is the actual length of the conductor, and they are not the same. So these are the equations that we derive and use for sag calculation. Is that okay? Do you have any question before I go to the next point, which is supports at unequal levels? Any question from you? Don't have any question. Now we're coming to the next stage where we might have supports at unequal levels. So if our land is like this, going from lower level to higher level, so what we can do, we have two supports. One support is from the ground to this point A, the other support is from here to this point B, and the conductor is strung between the points A and B. The conductor is suspended between the points A and B. Don't worry about that B prime for now. So conductor is suspended between the two supports A and B, and the lowest point is going to happen here at O. Again, lowest point is O again, happening here, but from the look of it, it does not look like it's the middle point of that span L. So what we do, we consider all the distances. So now what is happening here? Two different heights in terms of the distance between the support where the conductor is fastened and the lowest point of the conductor. So here we have delta 1, which is larger than this delta 2. So we have two sags now, delta 1 and delta 2. So delta 1 and delta 2, and this is happening due to the distance between the point of support and the lowest point of conductor is x, and this one is L minus x because that is L. So x and L minus x are causing two sags, delta 1 and delta 2. Delta 1 can be calculated using that formula, delta is equal to WL square over 8H or 8T. The same formula is used here, but the length is considered here to be double. For example, if we assumed, now I'm coming to the point of lead time, if you assume that this conductor A or B could be imagined that it is expanded to the D prime, then it's going to look like that parabolic method, and this point O, which is the lowest point of the conductor, will become the middle point of the conductor, meaning this distance x, if we convert it to a double one, or if we double it, then we can utilize that previous formula from parabolic method to make it simple and easy. So that's 2x squared. L is 2x now. So it's the same thing, L minus x. So 2 times L minus x is whole squared. And we use the same formula, WL square over 8t. And that is what we get. So we get delta 1 and delta 2 on either side. They are different. But if the land was plain, the towers are of equal height, then these delta 1 and delta 2 could be the same. That is why what we got in parabolic method delta, and that delta will be the same on either side of the lowest point of the conductor. We did not need to worry about what will happen on either side. It will be the same. Now, from the diagram, what we see here, that H is a difference between the heights of these two towers where the conductors are fastened. The conductor is fastened here on the structure of the tower. The conductor is fastened here at point P. So this is the H, which is the difference between the two towers. And if we use that one into our equation, we can see from the diagram that H is going to be equal to the difference between the two sides, delta 1 and delta 2. So H is equal to delta 1 minus delta 2. If we put those equations that we got there, delta 1 is equal to WL minus x whole squared over 2t. Delta 2 is WX squared over 2t. To put them in the equation delta 1 and delta 2, then we can get that H is equal to WL over 2t times L minus 2x. And from that equation, we write the equation in another form, just manipulating this one. We find x is what? X is now is equal to L over 2 minus TH over WL, because we are interested at the lowest point of the conductor from the perspective that we need to maintain the ground clearance according to government rules and regulations, and to make sure that we observe safety of all the people around all the time. So we want to see the lowest point of the conductor is point A or from point B of the two towers. So x is expressed as L over 2 minus TH over WL. Look at that equation. X is equal to L over 2 minus TH over WL. Now, if we look at this equation, if we arrive at a situation where L over 2 is equal to TH over WL, what is going to happen? If we imagine that the values of L, T, H, and W are such that L over 2 is equal to TH over WL, what is going to happen? Answer, that is not that difficult question that I asked. No answer from anyone. Anyone must answer. What is going to happen? I told there is no answer. What is happening? Are you hearing what I'm saying? Hello? Hello? I need answer from you. What is that it doesn't become parabolic? That's not what I wanted to hear. If L over 2 is equal to TH over WL, what happens to X? What will be the value of X? X is equal to 0. That is the correct answer, and that is what I wanted to hear. That is the easy one. Everyone should see that X is going to be equal to 0. Now we should come back to the diagram or the figure. If X is equal to 0, what does that mean now? If X is equal to 0, what does that mean now? We always need to remember one thing. We deal with equations, we deal with physical systems. We deal with physical systems, we go back to equations. That is what we do in science and engineering. So we got an equation that X is equal to L over 2 over 2 minus TH over WL, and X is equal to 0. And we go back to the physical system to see what does that mean now if X is equal to 0. Yes, that support is at the lowest point of the conductor, or it can be said in other words, the lowest point of the conductor is at the support. The lowest point of the conductor is not here in between two supports. The lowest point of the conductor is supposed to happen all the time in between two supports. But in this case, the lowest point of the conductor goes to the top of this support, which is at lower level. It won't go that side. Is that clear? This point O is not going to point B. The point O is going to go to point A. Is that clear? So if that happens, what does it mean again physically? The lowest point is happening here and the conductor looks like it's going to be like this. Can you imagine? If that's good. Now you imagine that you have a piece of conductor. You are two people, both of you are at the rooftop holding that conductor horizontally. And you both of you have the same height, holding the conductor at the same height. So you sharing the same load, you pulling it with the same tension to keep the conductor suspended between 2 points in your hands. Now one of you come down to the ground, and someone is still at the rooftop and holding that conductor. What is going to be the experience now? One is standing on the roof holding the conductor, the other person is on the ground and holding the conductor. What will be the experience now? To keep the conductor still suspended in the air in between two supports. What will be the experience? You need to answer. It's not difficult, it's easy. It's play. Answer, please. Yes, more tension at the top, meaning the person sitting at the top or standing at the top will have to pull it with more tension, meaning we have to ensure that we have more pulling force here. That's the first thing. Second thing, when we say that more tension at the top, we need to again go back to that working tensile and tensile strength of the conductor, we might consider the tensile strength of the conductor here, which is less, and the tensile strength working on the conductor will be more. We must not allow it to exceed its ultimate tensile strength. That is what is important when it happens like that. Right? So this is going to be the physical experience, and we cannot ignore that. We go to the next consideration. For example, if we find that L over 2 is less than TH over WL, what is going to happen? If L over 2 is less than TH over WL, then what is going to happen? Answer it. Negative X, meaning this point O actually is on this side. Right? Again, that uneven pulling force will come into the scenario. But F6, if X is positive, meaning L over 2 is greater than TH over WL, it will look like this, the diagram that you see here. Is that clear? And now you want to look at the economic span length. I think it's 50 minutes already, so we'll consider this economic span length tomorrow. If you have any question before we close for today.